determination. And so Leveson says that high reliability is neither necessary nor sufficient for safety, and she repeats this quite a bit in her work. And so there are many methods you can use to do based on system safety, which are system theoretic hazard analysis, system theoretic process analysis. So there are a lot of methods out there that can help you get started with this. I'm gonna go to lesson 2, shift from event-based to constraint-based accident models. So acknowledge that accidents are complex processes involving the entire socio-technical system. So if you're working on a system, reach out, think about, okay, what would the system look like in a societal context? What kind of disciplines do I need to understand this broader system? And then I think looking at system safety can really help you to see, okay, what kinds of disciplines, what kind of perspectives are maybe missing in my lens to understand safety properly. Shift from a probabilistic to a system theoretic safety perspective. Also, I think in machine learning, especially, we rely a lot on probabilistic notions, and these don't guarantee anything when it comes to actual physical or material safety of these systems once they're in working in the real world. So what we really need to think about are more like the fail-safe mechanisms. Maybe we have to assume that our system makes errors, but okay, what happens when those errors occur? Can we actually observe them? Right, so it's really important to have a process model where you have the goals, which include the objectives, but also the safety constraints, or what are the things that absolutely should not happen, and think about, okay, what are the ways that we can act? What are the observability criteria what things do we need to make sure that we see before it happens? And then the model condition is really more about, okay, what is our model of the broader process? Including what the role of human controllers would be. So this really also opens up, I think, an interdisciplinary space for many of the new emerging AI applications that we're looking at today. And it can really help to make it, I think, also more scientific. I think this is a process model is a great way to get started and say, okay, what is our current process model and what's missing there? And I think it can really help to get a better understanding of where work needs to be done. A few more left. So shift from a siloed design and operation of AI systems to aligning mental models. A lot of the work in system safety looks at the role of the operator, which is often underexplored, misunderstood. So operator error is often a product of the environment in which it occurs. So you have to look at the environment. There again are many important lessons that we can think of. I had examples here. My point here is we should not just look at the operator, we should look at broader at different kinds of stakeholders, impacted stakeholders. And one of the things we're doing now is looking at AVs, autonomous vehicle fleets, as a public infrastructure, and how we need to look much broader at, like, not just the driver, but also the cyclist, the pedestrian, if we want to understand what safety is in this context and how we engineer our systems properly. Okay, I think I might run out. I think I go out of time. There's 3 more left. Maybe this is a really important one. Curb the curse of flexibility. Highly reliable software is not necessarily safe, as we just heard already. Increasing software reliability or reducing implementation errors will have little impact on safety. This is really where I think a lot of developers are like, okay, what should I do? And unfortunately, many software, I'm quoting Leveson here, many software requirements problems arise from what can be called the curse of flexibility. So have a look at the curse of flexibility. Nearly all serious accidents in which safe software has been involved in the past 20 years can be traced to requirements flaws, not coding errors. The most serious problem arises, however, when nobody understands what the software should do or even what it should not do. And I think we're living in a time where systems are becoming much more complex. If we look at the largest models we see from 2012, when Nancy Leveson wrote her book, we had 60 million parameters. We're now, in 2021, we're at 530 billion parameters, and we're going towards 100 trillion parameters. Nobody understands, for a long time, nobody has understood how these models work, and we will never. However, we're using them in many sensitive contexts. So this tells you something to think about what we're up against. Yeah, I have to skip to the end. So think about not just about designing for a system itself, but also for the operation for using the system is an important lesson. That can also be seen at the Boeing 737 MAX accidents, where you see basically what Leveson says is that systems will tend to migrate once they're used towards states of high risk, and that's predictable. It can be prevented. And so with Boeing, we saw that they put new engines on their airplane under economic risk or economic pressure. They were trying to keep up with Airbus and other, other forces, and they made mistakes in redesigning their airplane. And this is something we see over and over again in history of software-based automation. And that brings us to the last question, last lesson around management and culture. So again, I will quote Leveson here to honor her work. The key to effectively accomplish any of the goals described above lies in management. And most people want to run safe organizations, but they tend to misunderstand the trade-offs required and how to accomplish the goals. And luckily, there is lots of lessons learned around building proper management, building a culture in which it's essential, safety culture, in which we are not focusing on blaming those that are making mistakes, but we're creating a more open and understanding environment to properly understand how the system behavior actually works, and to ensure that when we understand when something could go wrong, that we actually put it on the table and don't shove it under the rug. And this is a very big challenge, but it's essential. So with that, these are the 7 lessons. Here's a link to the piece. It's on archive. Thank you for your attention. Wishing you a great rest of the workshop. I don't know if you have time for questions, maybe not, but looking at you, Cynthia.
Thank you so much. Yeah, thank you so much, Roel. I think maybe we can take one question. I see Jose is raising his hand. Do you want to ask the question?
Yes, great talk, Roel. My question was about these curves of flexibility from software systems. And one of the things that we argue that makes AI different from classical software systems, they are even more flexible, they are more adaptable. And you put the example of GPT-4 perhaps coming or not this year. But if we just look at GPT-3, which is a frozen system, so one is you can train because one of the dangers, if you let the system learn while it is deployed, that's even more dangerous than having a system having trained and tested, and then you freeze it and you deploy it. But now we have realized that, for instance, with GPT-3 and some other language models, we will need years to understand how these systems work, and they are being deployed in many different ways. So we have a lot of flexibility, much more flexibility than we anticipated, even with frozen models. So how can we just balance this? Because if we think of AI not being flexible, that's a little bit like an opposition in terms or something like that.
Yeah, it's how can we do that? Well, I think it's good that it's frozen, right? So that's step one, but unfortunately, these systems are being marketed already, right? So there's already a strong business model around them. So I think we should regulate that as well. I think that's a problem, especially if you look at the impact it has. The errors that these systems make, we don't even know how to let them function properly. We don't even have like proper requirements for them because we see them as this kind of big general purpose technology. So I think it's not just about understanding how the system works. It's like understanding what do we want to do with it and what do we not want to do with it. So actually, this is where it becomes a steep challenge. But what you want, I think, is for every particular application, you want to have a process model. You want to really understand what the system should be, what kind of system behavior, emergent behavior is acceptable and what not. And yeah, of course, understanding the system is a prerequisite, or this particular component, this model is a prerequisite, but that's only step one. right? So I think I'm just arguing to take it to slow down, and and also for regulators to, at some point, to step in and say, okay, what are the actual harmful ways that these systems are being used already? So I think it's a bit out of our hands as like technical developers. That this is more of a policy problem, I think, at this point.
Thank you.
Thank you so much, Roel. So I think maybe we can proceed to our paper presentations then. Do we have authors from the first paper? Yeah.
Yeah, this is just support Ukraine. This is just the link. I wanted to share that one of my colleagues is from Ukraine. This is a verified fund. So if people are thinking about supporting Ukraine, this is a good place to go. Thank you, everyone, and stay safe.
Thank you, Roel.